Okay, good morning, everybody. So today we're talking about the Maxwell-Boltzmann distribution. It's the last topic in the kinetic theory of gases. Maxwell-Boltzmann's analytical expression, it's an equation which describes the speed of the molecules in a gas sample. So it's going to allow us to figure out exactly how fast things are moving. It's important because once you know this, you can calculate all sorts of things like the probability of finding a gas molecule at some speed, or the average speed, or whatever you want. And the Maxwell-Boltzmann distribution can be derived from a relatively simple set of assumptions. It's described in Atkins, but I'm going to cut right to the chase. The expression for the Maxwell-Boltzmann distribution is given right here. So if you're the kind of person who's taking notes, write this one down and circle it. I'll describe what this quantity is here, but it's related to the probability of finding a gas molecule at some speed u. So u is the gas speed, m is the molar mass, r is the ideal gas constant, and t is temperature. And I'll tell you how we use this, but first I want to make a couple comments about the equation itself. So if you were to plot it, you'll see that there are these two parts to it. And let's see if I can slide my little avatar over. So one part of this equation has this u squared dependence. It's a quadratic which goes up, right? And the other part has an e to the negative u squared. So that's going down. And if you were to actually sketch out what the distribution looks like, it's shown here, right? It goes up, reaches some maximum, and then it turns over in this asymmetric shape. So a couple important points. There's always a distribution of gas speeds, right? Gases do not move at one speed. There's a distribution. Some of them move very, very slowly. I can get my cursor to work. I swear to you, I have the most problems with my cursors. All right, forget it. Some of them move slowly. Some of them move very, very fast, right? There's a distribution of speeds. There's some really nice simulations of this. I'll put some links up in Canvas, which you can check out and play with. The second is that the distribution depends on two variables, really. The first is m, the molar mass, and the second is t, the temperature. Right? So it depends on those two variables. As you might expect, as temperature increases, right, the molecules move faster and the distribution broadens. So if you're at low temperature, most of the molecules are moving at a low speed with a very narrow window. And as the temperature increases, the average speed increases and the distribution increases. Opposite is true for molar mass. So as the molar mass decreases, the distribution broadens and shifts to the right. Moves faster. And I just want to make sure, I think I am recording this thing. Yeah, good. I am recording. So those are important things to keep in mind. Let's talk about how we use this. And here's the Maxwell-Boltzmann distribution, right? It's going up, it's coming down. What you might guess or infer is that the probability of finding a molecule in some range of speeds is related to the area under this curve, right? So the area under this curve is the probability. And mathematically, we associate areas under the curve with integrals. So the specific expression for the probability of finding some molecule between speeds u1 and u2 is given by this. It's the integral from u1 to u2, f of u du. If you start to do some math, you'll realize a couple things. So recall that one way we can approximate integrals is as tiny rectangles. So I could divide this integral up into a series of tiny rectangles. Each rectangle has a width, du, and the height of the rectangle, here to here, is the value of the maximal Boltzmann distribution, f of u. You start to do some units analysis. Excuse me. du is a speed, right? So this has units of meter per second. Probability, we know, is unitless. It's a number between 0 and 1. And if you do the units analysis, what you'll realize is that the Maxwell-Boltzmann distribution has to have units of second per meter, right? Then these two would cancel and you'd get a unitless probability. And on the surface of it, that seems pretty confusing. What kind of quantity has a unit of second per meter? But it turns out that this occurs a lot. So the Maxwell-Boltzmann distribution is formally what we would call a probability density. It has units of per meter per second, per unit speed. And it will turn out that probability densities are used whenever the variable of interest is continuously distributed. So if I have something with a continuous set of possible values like speed, time, distance, right? You have probability densities. When you have discrete possibilities, like rolling a die, then you have probabilities, unitless probabilities. And you can do some units analysis and verify that that is in fact correct, that the Maxwell-Boltzmann distribution has units of second per meter. Turns out that we don't actually use this expression a whole lot. Sometimes we do. We're not too often interested in the probability of finding, the molecules in some range. Instead, what we want to know is, well, what's the average of this whole quantity? And let me tell you now how you can find those averages. Here you go. The way you use probability distributions is as follows. For some quantity x, which is described by this probability distribution p of x, the average of x to the n, where n is some real number, is given by this expression. So we take an integral over all space. All space means all possible values. X to the n, p of x dx. And this, I suspect, looks pretty confusing. I have a little handout on Canvas which will explain to you where this comes from. I think it's actually a little bit more intuitive than you might expect. So check that out if you want to see where this comes from. But the critical thing is, can we use it? And so I just listed a couple problems here. Average speed. Right? If I wanted the average speed, what I'm talking about is this quantity here. And I should pause for a second and tell you what these brackets mean. In physics, if you ever see brackets like this, it means average, right? So this is the average speed. And I look at this, and you might infer that n is equal to 1. Right? So the expression for the average speed is given here, okay? It is now u to the first power, f of u du. I have to integrate this over all space, which means all possible values. In the context of gas speeds, the lowest possible value is 0, and the upper value is infinity. The average square speed, u squared. Well, in that quantity, n is equal to 2. And the average square speed is given by this expression. You can do this for integers. You could do it for something which was not an integer. So if you wanted the average 0.5687 speed, right, the expression would look like this. Right? This is the formalism we'd use. There's one other quantity that we're sometimes interested in. It's the most probable speed. I'm not going to look at it here, and I'm not going to give you the answer, although I will give you a hint. When you're talking about the most probable speed, what you're talking about is the maximum of the distribution. The maximum of that Maxwell-Boltzmann distribution is the most probable speed. And so what you need to think about is how we find the maxima of curves. Hint, hint. Some calculus. All right. One quick comment, and then I'll go to the final answer. Here's some expressions that we just derived. This is what I want, laser pointer. Here's my expression for the average square speed, u squared, right? U squared f of u du. Here's the Maxwell-Boltzmann distribution, f of u. If I start to plug these things in, you get an expression which looks like this, and the question is how you analyze it. And here's my advice. To solve these types of expressions, there's lots of different ways you can do it. Mathematica, calculators, Wolfram Alpha. But at least once in your life, you should go old school, right? You should use integral tables. It's what I learned on, and you should do it at least once in your life. So again, I have some additional background with regards to the Maxwell-Boltzmann distribution, which includes these integral tables, which are commonly used in the kinetic theory of gases. So practice doing that, and you'll get some experience working with these. It's actually a really useful skill. All right, putting it all together, at the end of the day, we can derive three quantities, or there's three common ones we use. The first is the most probable speed, which is usually called u star. Right? Again, u star is the maxima of this curve, and it is given by this expression here, 2RT over m to the 1/2. I can calculate the average speed, which is given by this expression here, 8 over pi RT over m to the 1/2. Last but not least, we can get the root mean square speed, which is the average u squared taken to the 1/2. This is actually the same quantity that we derived last time with the kinetic theory of gases. And what you find is exactly as you would expect. It's 3RT over m to the 1/2. So these scale as follows, right? Here's the most probable. The average is a little bit higher than that, and the RMS speed is even a little bit higher than that. You should get some practice calculating these things and deriving them and know where they come from. So I will stop here, check out the problems, check out the simulations, and I will see you next time for chapter 2. We'll start talking about the first law. Bye, everybody.